Okay, class, where we were on this chart right here. We were saying, we were looking at the slow oxidative fibers, which were also called, we said, slow twitch. We looked at the features of why these are slow, but they give endurance. We had come down to what the diameter was, and then we said these have a lot of mitochondria and a lot of blood vessels, capillaries. Remember to get that, a lot of blood vessels. They're very red. Why? Because they have a lot of myoglobin. Myoglobin is that red. Okay, so these would be more like your postural muscles, your leg muscles, stuff like that there. Okay. Let's go now. I'm going to skip this for right now. Let's go to the fast glycolytic, because this is what we primarily have in our human body, this and this. The fast glycolytic, let's say like the muscles, they're called fast twitch. Speed of contraction is fast. Myosin ATP is fast. Now when we went here, remember that means not good efficiency, breaking down ATP fast, but you want the contraction fast. So that's inconsequential as to how much goes away as heat. Primary pathway, anaerobic, glycolysis. We talked about that. Myoglobin, low, because you're doing anaerobic, and so virtually you would have not a lot of oxygen. Glycogen, a lot. This is also called white muscle. Oh, that's right. I forgot. Okay. This here, let's say if we were dealing with eating chicken or something. This here would be the red meat right here. The red meat, the dark meat in the chicken. Okay. This here is called red muscle. So let's see what it's called. Slow oxidative. Right here. Slow twitch, dark muscle, red muscle, several names. Over here, fast glycolytic. This can be called fast twitch, white muscle, because glycogen gives a whitish appearance. Let's go here. So you see fast oxidative. See how light it is? See how light it is? Slow oxidative. See how dark it is, that myoglobin? This would be this. This would be this. Okay. Recruitment order is the third to come. The third. Okay. Right. Slow oxidative fat, it would come in first. And then fatigable quickly. Okay. Now, what will happen is, I'm coming down here, white, glycogen, fiber diameter, large. See right here? Large. Why? Because all that glycogen you need. Right? Fiber diameter, large. And the other reason is, you don't have a good what? Surface to volume relation. You got the glycogen in there, the muscle is big, but your surface area is not that good. Mitochondria few, and this is few. Okay? So that's what we're looking at. That's what we're looking at. All right? Now, I want to come back to this. No muscle in the body has just this or this. No muscle. No muscle in the body has just this or this. So all muscles have a combination. All muscles have a combination. Now the difference is, if it's the biceps, you got more of this than you do this type of thing. All right, now we go to the middle one. The middle one is the fast oxidative. Now this one here, if humans had a lot of this, we could run the mile at the same rate you do the 100-meter dash. Speed of contraction fast. Break it down fast. But you're using aerobic. Okay? Myoglobin high. So everything really is similar to this, but a few things similar to this. This would give fast movement for long distance. Animals have this, some animals, but we as humans don't have a lot. Well, why? Because we as humans gave up physical ability for mental ability. We gave up physical ability for mental ability. Because we can build houses, we can make machines to do a lot for us, and so forth. Anyway, that kind of gives you an idea. So red muscle, white muscle. Red muscle, white muscle. Okay? Right here, we kind of talked about it, okay? So contractile velocity. Let's think about it. Contractile velocity. If you have a bunch of fast glycolytic, then it's fast. If the load is small, which means it doesn't take a lot because in other words, the minute you grab it, you can lift it. Okay? Now, so velocity is on this side. Endurance, though, is on this side. Predominance of slow oxidative. So faster velocity here. But as I start moving across this scheme, that means if you have a big load, your velocity is slow, right? Big load, your velocity is slow. All right? And what's going to happen is going to take a while to try to lift it. So you can kind of think on those things. Here's this picture. Influence of load, increase the load, increase the latent period. Now let's go back over here. If the load is increased, let me see if I can find something. If the load is increased, let's look at, then it's going to take a longer time before you reach enough, before you do enough recruitment, because you got to start, if the load is heavy, you got to recruit a lot more. So it's going to take a longer time. So your latent period is going to be longer to get before you can do the contraction. The contraction is not going to be, it's going to be a decreased contraction as far as lifting the thing. And a decreased duration. Okay, so here we go again. If you increase the load, the latent period is longer. The contraction itself, not the tension, but the contraction itself is somewhat decreased because you can't lift it. Contraction is going to be that shortening. Now think about it. In this case, the contraction is the shortening. So think about a 200-pound weight. And let's say you could lift it. That's an increased load. It's going to take longer to generate to finally get the recruitment to try to lift that 200 pounds. You're not going to be able to lift it too far up. And since you're having to use all your muscle fibers at the same time, you see what I'm saying? No spatial summation, all of them are having to be used. So using total temporal summation, then you can't hold it long because none of them have time to rest. None of them have time to rest. So that's the influence of load. Okay. We've already looked. Okay, so right here, see a light load, distance shortened, contraction. Because you can bring it all the way. Intermediate, not as far. Heavy load, you can't bring it all the way up. Right? It's going to be harder. Now, one reason it's going to be harder too, that this is what you have to think about. Now, I'm going to kind of hit you with another way to look at this. Okay. Now, remember, I'm going to go here. It's easy to do it in class. Remember when we did this here, let me find a picture that'll help us here. All right, use this picture. Now, remember to get the contraction, the myosin heads must attach to actin. The myosin heads must attach to actin. See how short those heads are? Now, let's think of something here for a moment. All right, we're doing a tug of war. We have 10 people on one side and 10 people on the other side. 10 people on one side, 10 people on the other side. Okay. Now let's say one side has everybody pulls back, but they can only go back so far because of their elbows and everything. All right, so they pull the other group closer to them. All right? Now, if the other group is closely matched, think about it, the other group is closely matched to the group that just pulled them, which of the 10 people can let go to re-grab to pull further back? See, if everybody's holding, those 10 have pulled you, but they hold it. Okay? But if anyone lets go to try to re-grab, the other group is going to pull it the other way. Now, the difference. If the group that pulled it is considerably stronger than the other group, then you can pull it and several people can let go. Some still have to hold tension so it doesn't slide back. Several people have to let go to re-grab to pull more. So what's my point? My point is that with a light load, you can unlock the myosin heads and re-grab further on the actin and pull in more and further more and further more. Intermediate, but with a heavy load, none of the myosin heads can let go. So that's the reason that if the load is, you can lift the load, but it's right at the edge of your strength, and you're lifting a weight off the floor, all you can do is just get it a little bit up, because none of the myosin heads can let go to re-grab and pull in more. Think on that. Think on that. So that's the reason for this here. Okay? And then you can see the velocity of shortening as you get heavier and heavier weights. All right. So we go further. Recruitment equals faster contraction. Why? Because you're bringing in more. If you can do recruitment. You can't do recruitment if you need all of them at the same time. See, these are thought things you want to look at. Okay? Now, what's the effects of exercise? Remember I talked about that. Aerobic exercise leads to increased angiogenesis. Remember we talked about the couch potato and the 26-mile marathoner. You increase the number of mitochondria. When you start exercising, see, mitochondria, remember when we did the cell, mitochondria have their own DNA. So the mitochondria amount can increase without the cell increasing. Now, if you stop exercising, endurance. Now, this is for endurance exercise. It's not strength building. Wait, this is running and swimming. Then if you stop exercising, those mitochondria will go away. Well, how do they go away? Because remember what you could do is autophagy in the cell. You can get rid of the stuff. Okay, they can be marked. Okay? They can be, ubiquitin will mark them and get rid of them. Increase myoglobin synthesis. Protein synthesis results in greater endurance, strength, and resistance to fatigue. If you do a lot of it, you may be able to convert some fast to fast oxidative. Okay? Humans can do it to a certain extent. Not a lot, but they can. Okay? Let's go further. Effects of resistance. This is kind of a weight. This is weightlifting. Now, this is swimming and running. This is weightlifting. Muscle hypertrophy. Remember we talked about increase the fiber diameter, but the reason is you increase the amount of actin and myosin. Increase mitochondria, myofilaments, and glycogen, okay, to try to be able to hold the weights longer and so forth. See those myofilaments? That's what I'm talking about here, to increase your strength. Okay, go further. Overload principle. All right, now I'm going to stop this video here, and we're going right here. So then we go into the overload principle, and then we'll go into something else. That overload principle is that you have to start lifting progressively heavier weights to get it done. Forcing a muscle to work hard promotes increased muscle strength, but you gotta make the muscle want to. It won't do it if you keep the same weights. They increase to the adaptive. And that's all I'm going to say on that. You got to increase the amount of weight in order to make the muscle make more actin and myosin. You got to increase the weight. Otherwise, it'll stay the same. That's the overload. A little bit above your load. I'm going to close here.